Hello everyone, here's another Physics 30 example. This time we're in Unit 5, which is Atomic Theory, and this is Lesson 1, which is to do with photons. So here we have some information about a photon. It's just a little wave diagram actually. So here we can see the wave propagating along an axis, and we're told that 650 nanometers is the total length of all these oscillations in the wave. We need to determine the total energy of 71 photons in EV. So let's take a look at what this this representation of the waves gives us. Well, hopefully you can remember that a wave is a full oscillation or a full period. So I'm going to break this into 1, 2, 3 waves. So this is 3 lambda, and the length of that is 650 nanometers. So that means one wavelength is 650 nanometers divided by 3. So the wavelength is 216.6 recurring nanometers. Okay. What we also know is that we have 71 photons, and we know that the total energy is going to be equal to the energy of a photon times how many photons there are. We're going to call that n of the energy photons. So we can very easily then figure out that the total energy is going to be 71, that's how many photons we have, times the energy of the photon, which is hc over lambda. And so we can just plug this in. We know, so we've got 71 multiplied by Planck's constant. Oh, actually, back it up. Planck's constant, remember we have two values for that. And since we're asked to find it in EV, there's a big clue there. I'm not going to use my 6.63 because that's joule seconds. I'm going to use my let's go 4.14 times 10 to the negative 15, because that's my EV seconds. That's my H in EV seconds. I'm going to keep going. I'm going to multiply this by the speed of light, which is 3 times 10 to the 8 meters per second, and then all over the wavelength, which I established to be over here, 216.6 recurring. That's meters. Oops, wrong color. I want blue. That's meters. And that's going to give me my total energy, which if I plug into my calculator gives me 4.0699, lots of other decimal places, and that's going to be times 10 to the 2 EV. Looking at my significant digits, well, the measurement I used was 650, and I'm told that it's 71 photons. I'll be tempted to say 2 significant digits here, but a photon is an integer number or a discrete number. So that's not going to count as part of my measurement or my significant digits. I'm going to use this one here. So it's 3 significant digits. So don't want to do that. I want to go 407 EV. And now I can just do a quick check of my my units here. My meters cancel out, my seconds cancel out, and I'm left with EV. Okay, so here's my second example. I'm told that I have a 90-watt lamp that emits photons with a particular wavelength or indeed a particular frequency. These are interchangeable. It's UV. We need to determine the maximum number of photons that would be emitted in 10 seconds. So once again, I'm remembering that the energy of the photon it's either hc upon lambda or hf, and it doesn't matter really for this one. I'm going to use hf because I've got both of these. I've got the f and I've got the lambda. So the energy of an individual photon, it's going to put that as ep, is h, and I'm going to go 6.63 times 10 to the negative 34 joule seconds. That's my h. multiplied by the frequency, which is 1.2 times 10 to the 15 hertz. Okay, so that's going to give me the energy of my individual photon. Let's put that in. That's 7.950 times 10 to the negative 19 joules. Okay, that's how much a single photon has. Okay, I'm then told that the lamp is emitting 90 watts. Well, 90 watts is the same as joules per second. So it's 90 joules per second, and it's left on for 10 seconds. So if I want to get the total energy that this lamp is emitting in that 10 seconds, I can just multiply out by the 10 seconds, because there you can see that the seconds cancels, leaving me with a total joule value. So that's going to be 900 joules. So the energy total in the 10 seconds is 900 joules. Okay, and then of course we are used to now using our formula, which, whoops, don't want to do that. I want to do this. Our formula is that the total energy is equal to the number of photons multiplied by the energy per individual photon. Okay, and since I know my individual energy number and I know my total energy number, it can come together and I can solve for n. So the n is going to be the energy total divided by the energy of the photon. That's going to give me n. And if I do that, I get 1.131, lots of other decimal places, times 10 to the 21. And there's no unit for that. This is just the number of photons. Okay, and so let me just double check my significant digits. I've got 3, 3, 3, and 3, so it's 3. Okay, so let's put that in. So it's going to be 1.13 times 10 to the 21 photons. There's my answer.